did it right because I got it says 0.7547 units and I got 0.737 units.
What was the z-score that you found?
That would have
I
been
got negative 0.39.
I got negative 0.38.
Okay. And that's not a huge deal. When you look in the z-score chart, when you've got an area, where do you look in the z-score chart to find the z-score? You say that again. So the z-score chart is designed so that if you look up a z-score, you look up the first decimal place and then you look at the second decimal place and where they meet, that's the area that's below that z-score. That's how that's set up. So of course if you're at negative 3 point something, you got very little area below you. As you move up from there, you're going to get more and more area as you go up. Sorry, I cut my finger on this chair somehow. That was awesome. Let's see. All right, there you go. Yep. Thanks. So on that last problem, 4B, it says find the time that would put somebody in the 35th percentile. Sure. So there's the 35th percentile. That's what it looks like visually, right? The 35th percentile means that you are at a position where 35% of the people or the other data or whatever is below you. The really nice thing about percentiles is the z-score chart is set up to understand areas that are below. That's awesome. The big mistake to make here is to look up 0.35 like this. There's 0.3. There's 5. There's 0.35. What's wrong with what I just did?
You're looking up. It's a value, not a z-score.
It's an area, not a z-score. So I can't be looking for z-score 0.35. I don't even know what the hell the z-score is. The 0.35 is 35%. It's an area. And for another thing, I think this is a point over here, it's going to have to be on the negative side of things. We know it's got 35% below, so it's got to be down here. So if I look at what's the closest I can get to 0.35, looks to be about right here. One of these two things here. Which one's closer to 0.35? We're not playing Price is Right. It's okay to go over. But in this case, which one is closer, truly closer? This one's only 17 away, this is 20. Now, if you average those out, little t here, that would be fine. That's basically right in the middle. When I took probability, when I took this, I had to actually interpolate. I had to come up with an equation to figure out how far in between these are. And screw that. You take the closest one, or if it's pretty close to being right in the middle, average the two out. Sort of like that 1.645 one that we saw last time, right? It averaged the two out. So I used 0.39 because that's closer. If you use negative 0.385, even better. I like that. That's cool. Yes, sir?
Could you use like algebra to find the z-score? Like put wait, never mind.
Yeah, we don't have enough information to do it that way, right? Okay. Now here's the other thing. We have a beautiful equation, and you would only hear a math teacher say that phrase. We have this equation that if I know an x score and this mean and the standard deviation, I can get the z-score. This is the reverse, isn't it? In fact, let me show you this. Let me see if you guys get this. A normal z-score problem where they ask me for a probability. They give me an x, I change that into a z, right? Using this formula. and then I look up the probability. I look up the percentage in the chart. You with me? And we're just getting into this, but this is going to become like the basic, being able to do 2 plus 3. This is the basic problem in statistics. Can you do this problem? Because then we're going to start tweaking this problem in different situations. So if you don't understand the basic one, how can you tweak it? So here's a classic z-score problem. They give me a shoe size, an IQ score, or whatever, and they say, what's the probability? It's more than that, less than that, whatever. We make it into a z-score. We look it up on the chart. Bam. Right? If they give me an area and they ask me, what's the score associated with that? What time would be required to put somebody in the whatever percentile? What IQ score would you need to be in this percentile, whatever? That's backwards now, isn't it? So I got to go this way. I look up in my z-score chart the area and the inside. I look out for the z-score, and then I got to convert it back to an x-score. And now you see why the hell you did the algebra that you did. Here's the little tiny bit of algebra that comes into this course. Can you take this equation and solve it for x? Of course you can, because I already did it for you for one thing. Right? If you pay attention to the key, it's right there. But doing that's not that big of a deal with algebra, is it? What would be the first step to solve for x? Multiply by sigma. And do you see why I'm doing this? This is a beautiful equation if I know all this and I don't know that. If x is what I don't know, I'd rather have an equation that says x equals stuff. Of course, right? So when we hit that problem in Math 90, when I teach this section on, where's the numbers? Why is it all letters? Why would this ever have anything to do with me? Well, okay, here's one place. If you need statistics, you better be able to manipulate equations so you can see what the hell to do. So you multiply that sigma up, and then you add the mean over, and you get this. Now here's the funny thing about this. What question will be on every single test? Who remembers? What's the z-score tell you? You're not allowed to write notes on your formula sheet, but the formula is a note. Look what this says. How do I get to a data point? I start at the mean and I go this many steps. Let me do it again. How do I get to this x? I start at the mean and I go this many steps. The z-score is the number of steps away from the mean to get to a data point. Now, that is exactly the same skill translating from French to English, Spanish to English, whatever. You with me? Because that is a foreign language staring you in the face. I just have to tell you how to translate that sentence into an English sentence, and I just did. So the better you're able to do that, the less you need to figure out a way to write a note on your arm or something. I'm telling you, you got a formula sheet, there's a note. That kicks ass. Okay, hopefully. Right now, what do we need this for? Just to be able to kind of complete this last step here. So when I look up 0.35, closest I get is negative 0.39. Negative 0.3, and then go up 9. So that's why on this paper here, z is negative 0.39. And now I just plug it into my little formula here. I know the mean, I know the standard deviation, and I want to go down 0.39 steps. So it makes sense algebraically. This is going to be this minus this because I want to be below the mean, right? Cool. So if it took you this long to find a parking place, you're in the 39th percentile. In this case, it's like golf. What's better, have a high score or a low score? Yeah, I want less time to find a freaking parking space. With me? Since they opened up the parking garage, things have gotten better, I think. Still not great. But it's a hell of a lot better it used to be, trust me. Instead of parking in a soggy soccer field. Okay. Any other questions from this handout? So this is the kind of problem right here that should become very soon easy. Like, please, Jeff, give me more of these kind. It should be very easy because it is. You translate the x score and give me into a z score. You look it up. And then you just got to make sure, is that the area I want? Is it 1 minus that, or is it that? Is the area below, or is it above, where I got to do 1 minus? That's not very intense math. Yeah.
How do you get the 17% in the line?
Here?
Yeah.
Because when I looked up negative 2.93, negative 2.93, I get 0.0017. Yeah. And then just move the decimal over a couple times. You can leave it as a decimal. You don't have to make it a percentage. But I thought a few of you guys would probably make it into percentages. Humans just like percentages better. Right? We're used to them. Okay. So any other questions from that handout? Okay. Cool, maybe. So let's try a couple more. Just make sure you got these down. With a prize. Okay. So let me give you a setup, and you guys try to work this out. Let's just try those two for right now. Start off.
Is that globally, or is that made up, or is that?
I think, depending on my memory, that should be the American male heights. The last time I checked. It's not quite right. We'll say it's island off the coast of America. It should be close. The fact that it's normally distributed is a fact. That is known. Please get used to drawing that picture. That should help you on these problems. Oh, sure. So this is also in the book on the very last page. Anybody else want a copy of the z-scores? Got a copy of the z-scores, you must bring it with you to the test. please call me over if you need some help. Negative 3.2. Is that right?
Yep.
So real quick, what did you guys get? Did you guys get negative 3.2 z-score?
Yeah.
All right. What do you do from there?
Look that up on your sheet.
Look that up, because that chart is some nice person calculating the areas for that funky ass shape. Because don't forget, probabilities are areas when they give me a visual look at the distribution. It's just the area that I want. That equation for a normal curve sucks. So somebody thankfully made that chart for us. I can just look it up. So what do you get when you look up negative 3.20?
0.0007.
0007? Okay. I'm a trusting fool. I'll go for that. Cool. You guys get that? 0.0007? So if this is correct, the probability of finding a dude that is shorter than 5'1" is 0.07%. How are we doing? Okay. Semi-consistent. Should make sense because we've gotten pretty far away from the average here, right? We don't expect a lot of people out here. We don't expect a lot of people way the hell up there. So that kind of jives with what we expect. So this probability is 0.07% if you want to make it a percentage. Okay. What about this guy here? 70 and 76.3 are both on that side of it. So I want that area there. This is kind of the worst problem because it's got two problems in one. How many z-scores do I have to calculate?
2.
I like it. The biggest mistake I see is people make one z-score. They say this minus this divided by the standard deviation. What is horribly wrong with that? What's part of the z-score formula? Your data point minus the mean. I've got two data points here. I can't just subtract them from each other. That doesn't make a damn bit of sense. It's all about how far away from the average you are. So I need two z-scores, two areas. So what do we get here? Let's see. Z equals, for this guy, 70 minus 69 over 2.5.
0.9982.
0.4.
The z-score, sorry.
Not that I looked it up already.
Point what now?
4.
0.4?
Yeah.
Okay. And then Z for the other one would be 76.3 minus 69 over 2.5.
2.92.
2.92? Being very trusting at the moment. So it sounds like everybody's got that. Cool. Are you guys getting this? One little thing I keep forgetting to say. If your Z-scores are coming out totally different from mine, number one, please say something. But number two, what's probably going on is you're not doing this. You're trying to put it in there all at once. If you put it into the calculator all at once, what does it see? It sees, oh, you want me to divide and then subtract it from 70. It knows order of operations. What's not fair for it is we can see the bar, it can't. Right? It has no eyeballs. Not yet. A few more years maybe. Scan this calculator. So you've got to put it in like that if you want to put it in there all at once. Or you can just do this equals divided by 2.5. That's perfect too. So be careful. If you're getting z-scores of 87.6, that's probably not right. So when you look up 0.4, what area do you get?
.6554.
0.6554.
554.
So is everybody cool with that? Did you all find that? Look up 0.40. Let me do it so I can just be a member of. Yes, I can. I got the same thing. What about 2.92?
0.9982.
0.9982?
Yeah.
Yeah, I like it. So how do you get this area in the middle that you want?
Subtract.
Subtract. Bigger minus smaller, please. Negative probabilities don't make a damn bit of sense. It's so unlikely. What, I don't know. It's gonna more than not ever happen. What the hell does that mean, man? So 0.9982 minus 0.6554, because if I take this much minus this much, I'm left with exactly what I want. So whatever that is. 3, 4, 2, 8. All right, I can subtract. So what does that mean? Physically, what does that mean? That's a nice number. What does it mean?
The area is 70.
Even more than geometrically. I mean, go back to what the problem is really about.
The probability that someone is between those two heights.
I
is
like it.
34.
So there's a 34.3% chance that any selected person is between these heights. Another way you could say that is 34.3% of the population of men is between these two heights. You with me? They mean the same thing. How are we doing?
That'd be unusual though, since it's more than 2 standard deviations above the mean.
This one?
Yeah.
Yes, a height of 76.3 inches is definitely unusual.
But there's 30% of people that would be counted. Oh, 'cause
In
70
between. Since you're saying in between, that's what makes it okay. Yeah. How are we doing?
How'd you say that? 34.8%
Of the population of American men, because that's what this is really about, would be between these two heights. So, for example, astronauts, do you know that they have a height restriction on who can become an astronaut? Or something that we all know is like jockeys. They obviously have a height restriction, right? Based on just you want to win, so you don't want to be too tall. You don't want to have too high of a wind profile. You want to be down there on it and not too much weight for the poor little horse. You with me? So if I want to kind of start a club somewhere, a jockey club, and I want to find out what percentage of the population would even be possibly able to do this, I could calculate that percentage here. You kind of with me here? I mean, that's a very weird example, but you start to see how this is immediately applicable to the real world. You don't get that very often in a math course where you learn something like, well, where do I use this? You use this immediately. This is being used right now, exactly this, no modifications. They're doing exactly this work. Okay, how much can I say that? I gotta stop. Oh, let's continue. One more question with this one. Find the height that would put somebody that's much better. In the, I don't know, 80th percentile. Another way I could say that is find the height that somebody would have to be taller than 80% of all other American men. Same means the same thing, right? So I could ask that same question a lot of different ways. So what's step one?
Find the z-score.
Good. Let's not get about it. Step one is draw the picture. So then I find the z-score. So step one, I draw the picture. A lot of you guys are going to skip this step. You've got to trust me that if you draw this picture, it will keep you from making very simple mistakes. You'll visually see that an answer you can't possibly go, oh yeah, I forgot to do 1 minus, because it's the other side. If you get so focused on looking up z-scores, you're not going to know what area you really want. So here, in this case, it's not too bad. I want the 80th percentile. Where's that going to be?
To the right.
It's got to be up here so that there's room to have 80% below it. What z-score do you find for that?
0.84.
Yeah, there's a definite winner here. There's a closer dude. 0.84 has 0.7995 area below it. That's as close as I can get on here to 80%. You with me? So if you look at 0.84, it's got 0.7995. That's the closest I can get to 0.80. All right, so far so good. What do I do with that z-score now to find the height?
Plug it into your z-score equation.
Yeah, plug it into that modified formula, right? I've got the z-score. Just look that up. I got the standard deviation. I can add that to the mean to get to my data point that I don't know yet. What height is 0.84 steps above the mean? We'll do 0.84 steps above the mean to find the damn thing, right? The formula is kind of silly. It just makes sense. It's what you would do. So the mean was 69 plus 0.84 times 2.5. 71.1? 0.1?
Yeah.
Okay. Sweet. So this is a really good place where you start to realize what I said, if you haven't realized it yet. The math in here is not intensive. The concepts are what's intense, right? It doesn't really, it's not perfect trade-off there, but just to let you know. Okay. So here's a little preview of the last couple sections. And the next time I'm going to have a handout where I've done some of the work that you have to do in 6.4, because 6.4 is a little weird, I will admit. That purple just doesn't want to go. It's like the 10th Doctor. So just to let you know, 6.4 is the heavily conceptual section. So you'll see in your homework how much homework I assigned from 6.4. Not much. Because it's really freaky. 6.5 is the nuts and bolts. The really funny thing is that it's going to take me a long time to explain this. But then in the end, what changes is one stupid little thing changes. The whole z-score, look up the area procedure, one little thing changes in there due to the concept of this. Okay. Here we go. So I'm going to go back to one of my favorite examples, and that was Florida's ages. So I used that before, remember when we were talking about Chevy-Davis theorem? Or Chevy-Chef? So here's the idea. How did this picture get made? Who remembered? This was the ages of people in Florida. How would I have made this picture besides, of course, just making it up? What would go into making? Why is it really tall there? What does the height have to do with the data? So how would I actually, if I had a blank thing like this and I started off, what would I do to make that picture? How old are you? I'm 2. I put a little dot at 2. How old are you? I'm 88. Okay, put a little dot at 88. Right? And then just, they build up. You with me? Okay, cool. So this is visual representation of individuals' ages. I seem to be making a point there when it's like, well, duh, John. But this is individuals' ages. The mean is right here. The standard deviation is whatever the hell it is. Remember, and the whole point with Chubby Dude was if you go one step out, you might not catch anything. Right? But if you go two, you definitely catch 3/4, so forth. Okay, so here's what do we really do in statistics, though? What do we normally do in statistics? What's the basic process of statistics? You have something you want to know, so you go and do what? To get a feel for it. I want to know what the percentage of people who smoke at Grossmont is. So what am I going to go do?
Take a sample.
Take a sample. I love it. So this idea of comparing, if I pick one person, what's the probability of this? That's not really useful. We normally pick more than one person. We normally pick 20, 30, 100. So I need the distribution that goes with every group of 100, every group of 20. I'm not going to just mark down one. I'm going to take a group of, let's say, 20 people. And I'm going to say, okay, get your average age. I'll wait. And then they tell me their average age, and I plot that. Pop. Then I go pick another 20 people. Average age, plot it. Another 20, average age, plot it. So this picture is going to represent groups of 20, every single possible group of 20. What is most likely going to happen if I randomly pick a group of 20 people?
You get closer and closer to the mean.
Be less specific. Physically, what's probably going to happen? Am I going to pick, is that going to be likely? Get 20 people right there.
No.
What's your average ages? We don't know, mister. We're what? Okay, sorry, I'll do it for you. Right? I'm not going to get a bunch of 1 and 2-year-olds. If I do this randomly, what's going to happen most likely? And what you said is going to be true, but why?
Different ages.
I'm going to get a mixture of both groups, right? If I truly pick a random sample, truly random, which doesn't mean I go to the mall and I pick people coming out of some store. That's not truly random. I'm going to miss some people, right? Truly random selection from Florida. The most likely thing is a mixture. What's the average going to be of that mixture? It's going to be close to the real average. If you average these people's ages with these people's ages, isn't it going to be close to the real average? In fact, if the average age at Grossmont is 27, and I go out and pick 20 people, what's your best guess for their average age? 27. That's the expected value. That's what you expect. Would you be freaked out if it wasn't exactly 27? Hell no. I'd actually be freaked out if it was exactly 27. Like I was when we did the coin flipping and we got exactly 8. That was a little freaky. But it should be close. So that's actually what's happening here. When I pick a group of 20, I should get a lot more people that are right on top of this average, a lot more groups whose average is close to the real average. So what's going to happen to this image is it's going to look a little bit more like this. All right, that's disgusting, but okay. So this is because of the fact that when I take 20 people, what's going to most likely happen is a mixture of the two. And I'm going to get average ages that are close to the real average. What is these little bumps for? Because what's the next most likely thing to happen? A bunch of people from right here. Or a bunch of people from right here, because that's the two big peaks, right? How are we doing? Now, what's happened to the standard deviation from here to here?
Decreasing.
It's getting smaller. I love it. The standard deviation gets smaller. Why? The standard deviation measures how far my data points are from the average. If when I take groups, more of them are close to the average, of course the standard deviation is going to get smaller. Now let me be a little more specific. This is the standard deviation for what? Now let me, again, we're just getting into this. Do not freak out if I've lost you about 5 minutes ago, because we're going to go over this again. But I need to get into this to get you start thinking about it. This standard deviation is for individuals. That standard deviation for this picture is going to be for what? Groups of size 20, the averages. I love it. That's why this gets this symbol. That is not sigma divided by x, right? That is sigma sub x. Sort of like, remember this formula from algebra? Oh, yes, you do. What did the little 2 mean? Do you remember?
The second value.
Or have you blocked that anymore?
Yeah.
The second value. It just means y2, the second y value. So all this means is the standard deviation for the means. Don't think that that's a little equation. No, it's one symbol. That's a subscript. It means the standard deviation for the means. Whereas this means the standard deviation for the individuals. In fact, in your calculator, who remembers this? When you do it in your calculator, doesn't it show you this?
Yeah.
Yeah, it does.
See how it didn't have a bar on it? So it's being very saying that's the standard deviation for the individuals. This is the standard deviation for the means of groups. Okay, cool. It gets smaller. That's interesting. What about the mean? Now I got a little off here. But if the average age in here was 26, and instead I took 2 people and then averaged all those, is it going to be different than 26? So if I take each of you and then average your ages, I get 26.
Yeah.
If I took 2 of you at a time and took your average and then averaged all the averages, is that going to be something else than 26?
Probably.
No. Let me do this again.
Well, we were taking all of them again, right? So it's going to be just 26.
It's the same people. You're the same people. If I take you one at a time and average those ages, I'm going to get the same damn thing. If I took you 2 at a time, took your average and then averaged everybody, right? 2, 2, 2, and then average those. So the average of the averages, the average of the averages of size 20 groups should be the same. It's not going to change. And what symbol do you think I use for this?
U sub
X.
x.
The average of the averages. And this is the standard deviation of the averages. And you're all going, oh, this sounds
So the
great.
only thing that is changing is just the standard deviation.
The standard deviation is the one thing that changes. Let me just tell you what it does. The new standard deviation, what I call the new standard deviation, is really the standard deviation for groups of size whatever. Becomes that. The old one divided by square root of n. Because the bigger my sample gets, the closer these should get to the actual mean. If the average age of gross spot is 27, I pick 20 people, I'd expect it to be close to 27 average. If I pick 800 people, I'm like, shit, that better be freaking really close to 27. I mean, good Lord, you picked 800 people. So the bigger my sample gets, the smaller my standard deviation gets, the less likely it is for a group to be really far away from the average. Okay, maybe. That is the one thing that changes in the whole z-score procedure. You don't divide by this in the z-score formula. You divide by the new standard deviation. And then you look it up in the chart and get the area. Everything else is the same. That's pretty damn nice. I think that's enough for now. So next time there's some more stuff to fill in here. Thank you.